The model of the all-electric cosmos provides new answers in all areas of cosmology. Answers which are in most cases far superior to those of gravitational models. But nowhere has this gap opened up more clearly in recent years than in the observation of comets. In the 1950s, the model of comets as dirty snowballs was developed. Here we see the influential astronomer Fred Whipple with a self-made, 250 kilograms dirty snowball. As a comet approaches the Sun, its ice is expected to melt, forming the comet's coma and tail. This idea reveals a very naive, almost childish conception of what is happening in space. In recent years, enormous progress has been made in the study of comets, and all observations speak against the model of dirty snowballs. Comets Wild 2 and Borrelly were photographed at close range and showed no ice on their surface. On the contrary, we can see sharp structures and craters. The first thing a melting lump of ice should lose is its sharp edges. So, as modern images reveal, comets are almost indistinguishable from rocky asteroids. In 2005, the electric model triumphed when making predictions about the outcome of the Deep Impact mission. A 370 kilograms copper projectile was to be shot at the comet Tempel 1 and the resulting crater was to be photographed. Since the projectile was, compared to the comet's size, nothing more than a mosquito crashing into a giant airliner, NASA scientists feared that they might not see anything at all. More optimistic predictions hoped for the creation of a cloud consisting largely of water and dust, but the comet's coma and tail would not change substantially. Overall, NASA expected only small changes. The Australian plasma physicist Wallace Thornhill, who elaborates on the model of the electric universe on his homepage, made completely different predictions than NASA. He foresaw a much more energetic impact than would be expected based on the mass of the copper projectile alone. According to Thornhill, the generated cloud would contain a little water, but would mainly be composed of a lot of fine, ionized dust. Furthermore, the activity of the comet should change significantly. In addition, Thornhill predicted a brief flash of light just before the actual impact, which must be viewed as a completely abstruse prediction in the standard model of dirty snowballs. When the projectile was finally shot at the comet, NASA was, as is the case so often in recent years, astonished and perplexed by the result. The explosion was so massive that the extra sensitively adjusted camera was completely blinded and could not photograph the resulting crater. The explosion covered an area of about 5 kilometers and resembled a nuclear explosion rather than a simple collision of a copper projectile with a snowball. The jets on the surface changed greatly in the wake of the impact, just as Thornhill had predicted. Furthermore, the explosion cloud showed too little water for the snowball model. Instead, a large amount of silicates was found in the fine, partially ionized dust, which indicates a rocky surface and was not predicted by the snowball model. The project manager of the Deep Impact mission said after analyzing the explosion cloud,
"That suggests the dust excavated from the comet's surface was extremely fine, more like talcum powder than beach sand. And the surface is definitely not what most people think of when they think of comets, an ice cube."
The lack of water was confirmed by another research associate.
"It's pretty clear that this event did not produce a gusher. The more optimistic predictions for water output from the impact haven't materialized."
The water was missing, but the amount of other ejected material surprised the scientists involved, who had expected a much lower energy impact. Professor Peter Schultz, one of the mission's chief scientists, said,
"If I had to choose just one surprising result from this encounter, it would be the amount of material thrown up."
And finally, the prediction of a first short flash of light, which seemed completely nonsensical in terms of a dirty snowball, turned out to be correct. Professor Schultz noted with astonishment,
"What you see is something really surprising. First, there is a small flash, then there's a delay, then there's a big flash and the whole thing breaks loose."
Now, how can the observations of the Deep Impact mission be explained in the electric model? We have already got to know the Sun as an anode in the galactic discharge process. The Sun's weak electric field extends throughout the solar system. It gets stronger the closer you get to the Sun. In the all-electric cosmos, Comets can simply be understood as rocky asteroids that are in a highly elliptical orbit. They spend most of their time in the outer reaches of the solar system, where they slowly take on the charge of the plasma there. Then, as they move through the increasing electric field on their way to the Sun, they begin to glow electrically due to charge differences. Their coma is a classical plasma sheath. It is elongated by the solar wind. Not surprisingly, comet tails typically have filamentary structures. The incoming copper projectile of the Deep Impact mission carried not only the kinetic energy, but also an electric charge that differed from that of the comet. When it got close enough to the surface, there was a first lightning discharge between the projectile and the surface. The actual impact was so extraordinarily energetic that electrons shot from a wide radius to the point of impact. The electrical activity of the entire comet's surface changed due to the new charge distribution. A member of the Deep Impact mission put it this way:
"The properties of the mid-infrared light were completely transformed after impact. In addition to brightening by a factor of about 4, the characteristics of the mid-infrared light were like a chameleon, and within 5 minutes of the collision, it looked like an entirely new object."
Understandably, the electrical explosion on the rocky comet did not result in a fountain of water, as some supporters of the snowball model had expected. The little water that was found was formed by negative oxygen ions in the explosion cloud, and positive hydrogen ions from the solar wind spontaneously forming water molecules. The Deep Impact mission proved beyond reasonable doubt that comets are not dirty snowballs melting due to the heat of the Sun. They are electrically charged, rocky asteroids that compensate for charge differences through incandescent discharges on their rapid journey through the Sun's electric field. The strong electrical discharges on the surface of comets mainly seek out elevated points. We know this from terrestrial lightning, which also preferentially strikes high objects. Protruding structures on comet surfaces are gradually eroded by the continuous discharges, a kind of electrical machining. Similar phenomena are known from plasma processing in industry and plasma physics. This is Comet Hartley 3. At its center, there is a sharply separated, completely smooth area that has been electrically eroded. In high places, and at the edge of the flat area, we can see the glow of plasma discharges. In this image of Comet Tempel 1, we can see glowing areas at the edge of a very smooth surface as well. These are probably not reflective spots, as NASA thinks, but typical plasma glow, very similar to what we know on Earth, for example as St. Elmo's fire before thunderstorms. Electrical erosion starts at elevated points, such as crater rims, and slowly flattens them. The eroded, partially ionized material contributes to the formation of the comet's tail. The rocky comets do not melt in the heat of the Sun, the electric erosion due to their movement in the electric field of our star eats away at them. If the electrical stress becomes extremely large, comets can also spontaneously explode or break into several pieces. We saw this, for example, with comet Shoemaker-Levy 9, which broke apart as it traveled through the electric field of the planet Jupiter. The remnants were sucked up by Jupiter and exploded in the atmosphere of the giant planet. The sudden illumination of Comet Holmes in 2007 also fits into the picture of electric comets. A dirty snowball that melts from the heat of the Sun alone cannot suddenly light up far away from the Sun. However, when an electric comet enters an area where the charge differences of the surrounding plasma are large, it produces a spontaneous, very bright glow. Another observation that does not fit into the snowball model is the X-ray radiation coming off of some comets. A snowball cannot, under any circumstances, produce X-rays. However, strong electrical discharges on the surface of comets are naturally capable of this. Sometimes comets come very close to the Sun and even crash into it. Of course, comets are tiny compared to the Sun. Their presence should have no effect on our star at all, as the standard model suggests, just as the small copper projectile of the Deep Impact mission should not have much of an impact on Comet Tempel 1. But just as the explosion of the copper projectile was enormous, so too are the consequences of a comet's approach to the Sun. The electric charge of a comet can cause additional stress in the plasma of the Sun's atmosphere and lead to the explosion of double layers. Here we have Comet Neat, which approached the Sun in 2003. During its flyby, there happened to be two powerful solar flares. This was by no means the first time that such a spectacle had been witnessed. In June of 1998, two comets approached the Sun at the same time. What followed was one of the strongest solar flares ever recorded. Also note the filamentary double helix shape of the ejected plasma. It's pretty obvious that there might be a connection here. But the scientists of the SOHO mission, who managed to capture these events, tell us the following.
A popular misconception is that sun-grazing comets cause solar flares and coronal mass ejections. While it is true that we have observed bright comets approach the Sun immediately before CMEs or flares, there is absolutely no connection between the two events. The sun-grazer comets, in fact all comets, are completely insignificant in size compared to the Sun.
As with quasars, that obviously exist in the vicinity of active galaxies, the public is urged not to believe their own eyes, simply because gravitational cosmology has no explanations for the observations. In 2016, another one of these allegedly completely random CMEs occurred just as another comet approached. These images are, as common sense and the all-electric model suggest, another strong indication that both the Sun and comets are electrically charged and therefore establish electromagnetic contact over vast distances. If, as the electrical model claims, comets are simply charged bodies moving rapidly in a plasma, then their outstanding characteristics, like a coma or an elongated tail, need not be confined to small rocky bodies in our solar system. If their glow is not caused by the melting of the ice of a dirty snowball, but is an electrical glow discharge, then planets, and even stars, can become comets as well. This NASA animation does not show a comet in our solar system, but the star Mira moving through the galactic plasma at high speed. Its tail is 13 light-years long. This star is a giant comet. To acknowledge the electric nature of comets would be to acknowledge the electric nature of stars, and thus the electric nature of galaxies. It would be a long overdue step towards a more realistic cosmology. But science is a human activity, and people like to cling to the old, the familiar, and, of course, careers, even if that means downplaying new observations and deceiving themselves and others. After the Deep Impact mission, NASA scientists presented a recipe for comet formation that, in direct contradiction to the observations, still shows water ice and dry ice as the main components. As strange as it may seem, but man's great curiosity is often overshadowed by an immense fear of the unknown. Apparently, this fear is strong enough to make people, who are confronted with such massive boulders and their sharp rocky craters, still see a snowball. A very special case of snow blindness.